So now let's talk about specific volumes in saturation. Let's study that a little bit further. Now, there's a memory trick that you need to know. If you go back to your saturated tables, or when you were there, you may have noticed that there are a bunch of properties, right? There's V sub F and V sub G. Those are the specific volumes of saturated liquid and the specific volumes of saturated vapor. Now, the F and the G subscripts actually come from German words, from what I've learned. I don't know what those German words are. I don't even remember now. But the way I remember which one goes with which is F reminds me of fluid, and yeah, fluid can be gas or liquid, but most of the time in our everyday language we think of fluid as a liquid. So F reminds me of a liquid and G reminds me of gas, and so I can remember which property goes with which, liquid or vapor, by just remembering F is for fluid and G is for gas. You may want to make a note at the top of all your saturation tables that F goes with liquid and G goes with gas. Now let's try to understand what's going on here. Remember, we had our saturated vapor mixture liquid and we added energy to it so that some of the liquid boiled off into the vapor phase. So I've shown a piston cylinder device here where some of the liquid has been boiled off because we've added energy, and so the specific volume of the system has increased, right? There's more space in it. There's more vapor than there was before. There's less liquid. Okay, so this is just two particular points under that saturated vapor liquid mixture region. Okay, it doesn't matter what 2 points, it's just we've added energy and boiled off more liquid. Well, let's think about this a little bit deeper. As a matter of fact, if we were to look at the specific volume or the density of the vapor in both state 1 and state 2, we would find that actually that ratio is exactly the same. The amount of mass in one little cube would be the same in both of these. Now, if we look at the liquid and we take a cube inside that liquid and somehow just extract that liquid and measure the volume versus mass in both state 1 and state 2, again we would find they're exactly the same. In fact, the way to state that mathematically is that Vg1 equals Vg2 and Vf1 equals Vf2. And this seems somewhat magical, right? How is it that those properties remain constant? Well, actually they have to. Remember that under the vapor dome, the temperature and the pressure depend upon one another. You can't have one change without the other one changing. That's the reason that you know, for example, that water boils at 212 degrees Fahrenheit or 100 degrees Celsius. But now I ask you, does it really? Well, that's only true at 1 atmosphere. If you reduce the pressure, in fact, the water will boil at a lower temperature. Or if you increase the pressure, the water will boil at a higher temperature. So specific volume is just another property, and specific volume then has to also depend on the other properties, like the fact that the pressure is already set. We're at boiling, where we have 2 phases, and so by Gibbs phase rule, which I don't remember if I have that in this class or not, but anyway, the point is that all the properties depend on one another when you have 2 phases present, and you can only specify one of them, and that sets all the others. So if you're at boiling and you have 2 phases and you've set one of the properties, that's it. The specific volume, the entropy, the internal energy, all those things have to be constant in the vapor phase and in the liquid phase. Now, the quantity of vapor and liquid can change, and in fact that's really the only difference between system 1 and system 2. So if we look at the average specific volume, okay, so if we take the total volume in the system and divide it by the total mass, now we'll see a difference. The average specific volume in state 1 and state 2 are different, but only because the quantity of vapor and liquid have changed. Okay, so the properties of the vapor itself hasn't changed, and the properties of the liquid itself hasn't changed. It's just the amounts of those things have changed. So mathematically, Vg1 equals Vg2, Vf1 equals Vf2, but V1 will be less than V2. There will be more volume in state 2, and assuming no mass is leaked, for the same mass. Therefore, the average specific volume will be greater in state 2 than in state 1. Now, one thing to note about this is that we somehow have to track how much of each there is. If the properties don't change, well, that's great, but how do we track them? As a matter of fact, before we talk about that, go again to the saturation tables in your book, and what you'll notice is, given a saturation temperature or a saturation pressure, you can go over and read off immediately what the specific volume of the liquid is and what the specific volume of the vapor is. And it won't matter how much of each you have. If you're at boiling, in other words, if there are 2 phases present and the pressure or temperature is set to one variable or one value, then the other variables have to be known, or just because of the nature of the way that chemical behaves, it will naturally cause its specific volume to be what's listed there. Of course, we're talking about water in this case. But back to keeping track, we have to somehow know how much of each. Remember, one of the big things that engineers do is simply quantify things. We count them, right? And that's one of the big strengths we have. Now, the total mass in either one of these systems is the mass of the liquid plus the mass of the vapor. So we can write that as an equation. M sub T equals MF plus Mg. Now let's define a new variable. We will call it quality, and we will give it the symbol X. Quality is nothing more than the mass of gas we happen to have over the total mass in the system. That's all it is. So it is a number that will vary between 0 and 1 when we're in the saturated vapor liquid region. In other words, when we have two phases present, the quality will be somewhere between 0 and 1. 0 simply meaning we have saturated liquid, there's no vapor yet, because the mass of the gas is 0, so it's 0 over the total mass, which is just 0. Or if we're at the other extreme, where the last drop of liquid has boiled off and is in the vapor phase, then all of the mass is in the gas phase, so Mg equals Mt, and Mg over Mt then would just be 1. Now, quality has no meaning in the subcooled region if we're not near boiling, and in the saturated region if we're not near condensation, then quality means nothing, because there's no potential for there to be two phases. But when there can be two phases, or there are two phases, quality has a meaning. So quality varies between 0 and 1, and it's simply something that allows us to keep track of how much of each of these we have. Now, what I really want you to key in on from this slide is the fact that the specific volume of the liquid is a property. In other words, it's a thing determined by the behavior of the particular chemical. Let's use water in our example. Not by anything else. So once you say you've got two phases and you've already specified, say, pressure, for example, well, then the specific volume is fixed. It is one value, and it won't be anything else. So we can define something called the lever arm rule. You see, here's something I didn't tell you. Remember, we were going through the terribly exciting movies of How Water Boils Part 1 and Part 2, right? And we went from saturated liquid to saturated vapor. Well, as we moved along, I said, well, the specific volume of the system increases, and away we go. And I didn't point out the fact that actually no molecule or no bit of water inside of that system has the average specific volume. As a matter of fact, all of the liquid remains at the specific volume Vf, and all of the vapor remains at the specific volume of Vg. All that happens is the quantity of liquid that we have decreases, and the quantity of vapor increases as we add energy to the system. And so what happens is the average specific volume goes up, but no water in the system, whether it's gas or liquid, has that specific volume or that value of specific volume. So really all we're doing when we say average specific volume is we're talking about how much of each of the phases we have, aren't we? So we can use something called the lever arm rule. And the lever arm rule is really important. Now, it doesn't matter if we plot pressure or temperature as the y-axis, but we'll need specific volume, or we'll begin with specific volume as our x-axis. It turns out we can put other properties in there as well, but we'll always leave pressure or temperature as the vertical axis and other properties as the x-axis. Let's start with volume because it's the easiest one to understand. So if we know our average specific volume, and we know what the specific volume of saturated liquid and vapor are, then we could calculate the ratio of the difference between the average specific volume at B and the specific volume of liquid, Vf, and the distance between Vg and Vf, point C and point A, right? We can take that distance ratio. So taking those two differences, so the length between A and B would be V average less Vf, the distance between A and C would be Vg less Vf, and we could use that as a rule. It turns out that ratio will simply be quality. It'll be X. Let me prove it to you. Let's start off with a simple equation. The total volume in the system is the volume of the liquid plus the volume of the vapor. Okay, fine. We know that the total mass times the average specific volume then is also the total volume, because that's really just the definition of V average, right? Okay, so if you need to pause the video along the way to keep with me, please do. You may need to slow it down or pause to think through this. But we're just re-representing the total volume by writing M sub T times V average. where understand that lowercase v is the average specific volume of the whole system. Now, to replace the volume of the saturated liquid, we're going to write MF/VF, the product of those two. In other words, however much mass we have in the liquid phase times the specific volume of saturated liquid, which is a property we can look up, would actually represent the specific volume of the total volume of the liquid. We can do the same thing for the gas. So we're going to replace capital V sub G in the original equation with M sub G, V sub G, the product of those two. Now we can also write what I would call a mass balance. The total mass in the system is simply equal to the mass of the liquid plus the mass of the gas. That's the total mass. And if we rearrange that equation, we can write the mass of the liquid, M sub F, as the total mass less the mass of the gas. Now, why would we want to do that? Well, we're going to substitute for the mass of the liquid. We're going to get that out of the equation. We're going to get rid of one variable. And if we do that, just rewriting the volume equation, you'll see that the only change I've made here is MF has been replaced with MT minus MG. So that's not really a big change. Now, if we rearrange this a little bit, if we decide to divide both sides of this equation by the total mass, notice it'll disappear from the left-hand side and appear on the right-hand side in the denominator. Now, notice the second term has mg over mt. Do you remember what that is? That's just quality, isn't it? Okay, so we'll see that here in just a second. But notice the first term on the right-hand side. We've got total mass minus mass of gas over total mass. Well, from fractions, you can just take mt over mt, and that's 1, minus mg over mt. Okay, we just separated out the fraction, no big deal. But again, now we have two ratios that are mg over mt, and those can be replaced with what we defined as quality. If we do that and then rearrange the equation to get the x's together, you end up with this equation that says that the average specific volume is equal to VF plus the quality times the difference between VG and VF. Now, why is this so important? Actually, it's very important because notice VF and VG are things we can look up. We have tables for these things. So if you know the quality and you know that the system is at some saturation state, right, some particular pressure or whatever, then you can look up VF/VG, you know the quality, and you can then calculate the average specific volume of the system. This is a very handy thing, okay? Now you can say, well, wait a second, that doesn't make sense. How would I know, say, the quality? Well, I would have to give it to you, or I'd have to give you average specific volume and tell you to calculate quality. You can work this equation back and forth. But the point is that VF and VG are just properties of that particular chemical substance, in this particular case water, and you can look those up in the back of the book. Now, the difference between VG and VF is usually just called VFG, and since we use it so often, it is tabulated in the back of your book. I think it is. Go look and see. It should be in the saturation tables. I don't have my book open right now. And there's some things in our book, 220, that are not in the book for 320 and vice versa, so I kind of get the two confused. Now, a lot of times we don't write the equation the way it is there at the bottom of the slide. Rather, we write it as you see it up in the box. So if you understood all this, great. Here's what you really need to know. Those equations that I have in the upper or in the right side of the slide, all in the box, you need to copy those. I would suggest you copy these down in the front of the book or in the back of the book, or and maybe even in the saturation tables, because that's where you'll use it over and over again. So I highly recommend copying this down. Turns out we also have saturation tables for one particular refrigerant. It's R134A. If you're writing these equations in your steam tables, I recommend you also write them in the refrigerant tables. Okay. Now, the first two equations there are actually the exact same equation. It's just one is solved for the average specific volume, the other one is solved for quality. If you want to rearrange it and check that that's right, you can. It's just a little bit of algebra. But in general, we don't have to use specific volume. We can use any property. We can use enthalpy. We can use internal energy. We can use entropy. Now, I'm not going to tell you what those things are quite yet. I'm not going to tell you what entropy is. Energy, hopefully you get some idea of what that is. That's the thermal energy in our case per unit volume, or excuse me, per unit mass. Enthalpy I'll describe for you in just a bit. But in general, Y represents any particular one of these properties we wish to put into the equation. It turns out that this works for any property you want on the x-axis. Now, not pressure and temperature, but any of the other properties.